let's first try the audio. Everybody hear me well? Yes, good. So, let us start. And in France, we are very fond of abstraction. This is famous. And certainly one of the reasons why France is very proud of being the country with the highest ratio of field medalists per inhabitant in the world. Why do we like this abstraction? Well, it's part of the spirit. It's powerful. And let us start talking about abstract things with a quote by Faraday. You know how in his talk described with such passion about Faraday's work and him being the greatest scientist that one could dream, etc. There is a nice anecdote about Faraday of him receiving the queen in his laboratory, and she wonders, why do you do all this and all this chemistry, whatever, etc. And answer of Faraday allegedly is, I don't know, but when people find what it is useful for, you can tax it. And this prediction has been realized so much more than expected. Nowadays, science, originally theoretical science, has generated enormous amounts of economics. You know, going over the cliff and paf. Okay. So, no reason then that science nowadays gets into the economic-oriented journal. And actually, it was a big marvel when the readers of the Wall Street Journal one day in 2009 discovered the results of a study made by an institute specializing in job market and asserting that best job in the world was mathematician. You see, here in this picture, the illustrator put a beautiful smiling mathematician and very poor lumberjack, because this was supposed to be the worst job of all, at least in America in 2009. And by the way, they made the ranking again in 2014 and arrived again at the same conclusion, mathematician number one. We thought that mathematician was a job for nerds, a painful job in which you are isolated, alone, and no success with the girls. Now, how come they say it is best job in the world? Because mathematics is growing in every direction and field. Yeah, this was Faraday. For instance, at the last International Conference of Mathematicians in Seoul, 2014, this is the big event gathering thousands of mathematicians around the world and the event at which the Fields Medals are awarded. For the first time, there was a plenary lecture about artificial intelligence by Emmanuel Candes, and it was for a special field of mathematics, and Candes was explaining us how with his work he had gone on collaboration with medical doctors from some hospitals and worked with them to improve the device. This is nuclear magnetic resonance device. Basically, it makes a Fourier transform of your body. These are the famous formulas of Fourier transform established by Fourier at the beginning of the 19th century, long before these kind of instruments were invented. Fourier transform is not very appealing a priori. For instance, this is a beautiful Lena that all researchers in image processing use as a benchmark, and this is the Fourier transform of Lena, which is less attractive. However, the Fourier transform for a mathematician can be very attractive. It's a very robust way to represent the signal. It has somehow a lot of redundancy, if you take it well. It was shown by Candace and collaborators that you can destroy up to 98% of the data of the Fourier transform, and still, if you do it cleverly with some intelligent tools, recover the original image with almost no difference that you can see. You have to be clever for that, but that's what mathematicians are paid for. And Candace showed, using these techniques together with the medical doctors, how you can make a much coarser analysis with the magnetic nuclear resonance and still be able to reconstruct the data with the great accuracy needed for the surgeons to examine. As a consequence, the time that had to be spent in this device was divided by 8, which is quite important, especially when you have young kids, that you don't want them to spend too much time in these devices. So it's one example of one of the recent directions of mathematics, collaboration with medicine, and it has been growing a lot. Another example of collaboration of mathematics with medicine is this device, the artificial heart, which has been developed by the team of Professor Carpentier for 2 decades now. And one day it will replace the heart transplant as a way to cure the very, very serious disease. Requires a lot of effort. Of course, it's basically medicine and chemistry, you know, these things, material science. But for this, you also need some very fine algorithms. There has to be good mathematics in this. And it's the same for every significant technological project nowadays. Mathematics has also been a revolution in culture and, you know, leisure industry. For instance, in the movies. This is a picture from famous movie Gravity, which won a number of awards. And it required years and years of preparation before the movie to, you know, devise the software that would be able to recreate the effects. In the movie, essentially, everything is artificial, except for the faces of the actors, basically. So everything you see in this picture is artificial, has been computed with beautiful software, and for this, you need good mathematics integrated in the software. Let me note that also in this, you see the power of mathematics as a way of creation. Mathematics is something that not only enables us to understand well, but also can recreate a world. And you may, for instance, decide that you want a new world in which the laws of physics are different, like suppress the gravity. For instance, another example is that in the cartoons, in movies, very often when there is hair rendering of heroines with long hair is all a big thing. Like in games like Final Fantasy or in movies like Brave and so on. And there are mathematical models to describe the motion of the hair, which is not the real one, but adapted, transformed. This is another example in which you create a new world with different laws. Also, mathematics has made its way into the arts, in particular architecture. This is a picture of the Louis Vuitton Foundation in Western Paris. It was a big deal in the art community when it was inaugurated. This was by architect Frank Gehry. But look at this weird building. If you make a building like this, with all probability it will collapse immediately. Except if you first check with careful software that it will stand up. And this means simulating all the forces and tensions which are around the building. 20 years ago, the software was not enough good to handle such things. There was need of progress in many fields, but in particular, mathematical algorithms for this, at the interface between mechanics, computer science, and mathematics. So this explains why mathematics has become a more and more important tool and field for all kinds of application. However, let us not forget that one of the main drivers for being interested in mathematics is curiosity. And it was very well said also very eloquently by Professor Rao, how you can be so happy if you are just passionate with the problem of understanding and discovering the truth in the world. And this has been going on for centuries and centuries. Look at this famous painting by John Wright of Derby. Famous because it describes science in the family, in the house, and it describes the joy of science like these children who are busy listening to a lecture by a scientist, they say the philosopher in those days, explaining about the solar system on a device which is called an orrery, which is a device that mechanically reproduces the motions of the planets around the sun. So, main motivation in this is the joy of understanding the beauty that there is in the world and the laws which are underlying them. And for them, this joy is not motivated by the need to get money, but just by the pleasure of understanding. And when you study such subjects, it can be at any level of sophistication. But the more you study it and the more you discover how difficult it is, natural sciences are always difficult, and the degree of sophistication that you have to reach to understand it in depth can be somehow frightening. But also, it's the amazing thing about the power of mathematics and abstraction that it works so well to describe our physical world. Let's continue with a quote by Faraday. When Faraday received the treatise by Maxwell, in which Maxwell was putting into equations the experiments of Faraday, Faraday says that at first he was almost frightened when he saw so much mathematical force made to bear upon the subject. Faraday indeed had no mathematical education. What do these formulas mean? And he found it amazing that these abstract symbols and formulas were containing all the important truths that he had discovered through experiments with the physical material. And this is one of the great mysteries and beauties of the human work, to have made these abstract structures represent and understand our world. So in my lecture, I will tell you about some of the mathematical concepts which have been used for a certain problem in mathematics, in which I made part of my career. This was not the only problem on which I worked, but it was one of those that occupied me most. Problem of understanding the long-time behavior of a classical problem, classical system. You have a system in mechanics obeying certain laws, and you ask in a very, very long time what will be the state of the problem. And this is a very old subject in the story of mankind, and I will review first the classical theory of this on the most famous example of mechanical system, which is the visible universe, that is, planets and stars. This was one of the early motivations of mathematics, by the way, in various civilizations. Let us describe the tools, find the tools that will enable us to make predictions about the motions of the stars. The ancient Greeks were extremely fond of this subject. And they had a big problem, not so much with the stars, but with the planets. The planets, they call the wandering stars. They go around because, different from the stars that always go in the same directions, planets go sometime in one direction, sometime in the other. It looked very strange, especially as the Greeks had this conception that since everything up in the sky was perfect, it should be described by perfect shapes, which can be only the circle. But motion on a circle always goes in the same direction. It never goes back and forth. To overcome this problem, they had the ideas to combine circular motions. And this was most famously used by Ptolemaios, probably the greatest astronomer from the ancient times, in his system of the solar motion, of the planetary motions. In that work, he combines 40 circular movements to explain all of the observations. For instance, you see, if you have a principal circular motion and you add some secondary circular motions on top of it, you are able to describe a motion that from time to time goes backwards. Nowadays, when we think of this and we look at this, we say, oh, 40 epicycles. This was quite complicated. And we know that, in fact, the solution is quite simpler. But for his time, it was outstanding. And if you think about it, with a little bit of stretch of imagination, you can say, after all, this was an ancient precursor of Fourier analysis. Now we know that every signal can be decomposed as a combination of circular motions, or if you want, of projections of circular motions, which are sine and cosine functions at various speeds. For instance, this signal, which apparently is nothing interesting, is just the combination of 4 sine functions with various amplitudes and various periods. So by combining the circular motions, you do get the sophistication that you want. The work of the Greeks essentially remained the best that one could think of for something like 12 centuries. It is amazing if you think about it. There were some improvements, but nothing dramatic until the arrival of Kopernik in the middle of the 16th century. And Kopernik understood that you can simplify the description by putting the sun at the center of the system and get a simpler description. Not so simple because Copernicus still used the epicycles, but he needed less than Ptolemaios. This was the first dramatic revolution, and nowadays people often speak of Copernican revolution when you turn from the idea that something is central to the idea that that thing, after all, is not central, and that it is something quite common. Okay. The next big improvement came about half a century later with Kepler, and that is a golden age. With Kepler, the description of the solar system becomes simpler than it ever was before, but also simpler than it will ever be after. It is the perfect solution, and that's the description that we still learn to this day in high school, the Kepler laws of motion. Kepler is very difficult to understand when you read it in the book, in his books. Very obscure, very mystic. You know, some of the greatest scientists were completely irrational. Science is rational, but the scientists often are irrational. And Kepler was a very irrational man. But he found these beautiful laws. First law is that the motion of the planets is not circular, but elliptic. An ellipse is this geometric shape. You find 2 points, the foci, and you look at all the points such that distance to the first to distance plus distance to the second is a constant, like on this. Blue distance plus red distance, the sum is always the same. This is an ellipse. It's very easy to draw, and the Greeks knew it very well. What Kepler discovers is that the trajectories of the planets are ellipses. Second discovery, the motion is not uniform. But there is something that is uniform, that's the speed of variation of the area which is covered. You see, viewed from the sun, when the planet goes from here to there, there is a certain area, a certain surface. And if the surface is the same here as it is here, here region A and region B have the same area, it means the time to go from here to there is the same as to go from here to there. In other words, the variation, the increase of the area which is covered, viewed from the sun, is constant speed increase of the area. And third law may be the most beautiful because it's an algebraic relation. It tells you that there is a proportionality relation between the square of the period and the cube of the distance. Here, t is like the time it takes the planet to go around the sun, while a is something like the mean distance from the planet to the sun in a certain way to compute this mean. And so there is the square of one is in proportion to the cube of the other. So if we use the Earth as a unit of measure, and here on this column, these are the years of the various planets, like Jupiter is 12 Earth years to go around the sun. And you compare, and on the other column you put the distances. Well, the squares of these numbers will be like the cubes of these numbers. Beautiful algebraic order within the solar system. And what the Greeks thought of as something which wanders, which errs, in fact what was very much ordered. Next comes the most dramatic moment in a way. From the Greeks to Kepler, things become simpler and simpler. From that moment on, things become more and more complicated. And first with Newton. Newton discovers this when he was very young, that you can explain all the motions of planets with just the force between them. And well, the idea that between the sun and a planet there is a force. That force is proportional to the product of the masses divided by the square of the distance. G is the gravity proportionality constant. Okay. And what is beautiful is that with just this law, Newton is able to recover the three Kepler laws. Ellipse, constant increase of the surface, and the relation between the times and the distances. But Newton goes even further. He understands that it's not just about planets and stars. It's about everything, everything that exists, everything that has mass. So that there is a force between this and me, there is a force between the Earth and us, and so on. That's why it's called the universal law of gravitation. Before Newton, everybody believed there was something special about the planets. And Newton says nothing special. Anything that has mass will feel this attraction. By the way, finding this inverse square law, when you understand what is a force and when you understand the Kepler laws, is very easy. Because in terms of physical dimensions, an accelerated force is proportional to acceleration. Acceleration is like a distance divided by the square of a time because it's the variation of the velocity, second variation of the length. And if we remember that in this problem, the cube of the typical distance is proportional to the square of the typical time, then distance divided by square of time should be proportional to the inverse of the square of the distance. So 1 over r squared, once you get the force, you find it, you understand it. But the genius, stroke of genius, was to have the idea to describe everything in terms of force and say that the most important thing was the acceleration, the variation of speed. This came with a dramatic discovery of differential equations and infinitesimal calculus. And this idea that you can predict the evolution of physical systems by solving differential equations, telling you about the tendencies. Einstein himself considered this as the most important discovery in the story of physics. It was shared between Newton, Leibniz, Lorentz, but most famously cast beautifully in the book by Newton about natural philosophy and mathematical principles. By the way, Newton. Here is another example of an amazing scientist who was completely irrational. And you know that he spent years of his life studying alchemy and in very mystic considerations. Anyway, at the same time as he found this, Newton was very proud of having found a single law describing everything, but also very much afraid by the consequences. Why is that so? Simple. If the law of gravity is universal, this means that not only does the sun attract the planets, but also each planet attracts any other planet. So if the Earth was alone in the universe with the sun, the trajectory would be a perfect ellipse. But since there are other planets, they will disturb the trajectory. It will not be an ellipse. It will not even be a closed trajectory. This will maybe a disaster. When everybody interacts with everybody like this, what physicists will call a multi-body problem, an n-body problem, it may be very complicated. Even if there is just one law, the fact that there are many players makes it very tricky. To convince you of this, I will show you a short movie, numerical simulations of motion of stars and galaxies by astronomer John Dubinsky. So simple, you will see a bunch of stars. Okay, in a real galaxy there are hundreds of billions of stars. Here there will be less, but it will give you the idea of the motion of a galaxy. Sped up enormously, of course, and there is only one law which is here, that is the law of gravity. And you will see the motion. What a big mess. It's beautiful though. When you're a scientist and you look at this, you think, okay, what can I say that would be intelligent about this? You ask even, what is the question that I may ask, and that it would be interesting to answer to understand this? This is still puzzling to these days. There's no more physics in this than the Newton law, but we are still at a loss to understand really what happens here. Oh, look at this beautiful picture of two galaxies colliding. Apparently, this is what will occur to our galaxy in a couple of billion years. And again, only the Newton law of gravity, and such a complicated phenomenon that we are still unable to describe accurately. Let us, however, point out that we have an advantage with respect to the video that I just showed you, is that the solar system is not like a galaxy. In the solar system, the sun plays an enormous role, and we should be able to take advantage of this at a qualitative level in the solution. Let us keep in mind that in celestial objects, scales are very diverse. Look at this. These are some planets that are familiar to us. Already the size of Jupiter is so big compared to the Earth. I think that the Earth, the entire Earth, would fit in the great hurricane that is always active on the surface of Jupiter. But even Jupiter is negligible or almost compared to the Sun. Look how enormous the Sun is. Actually, if you take the masses of all the planets together, it is like 1/1000th of the mass of the Sun. By the way, notice as a side remark that the Sun is not a big star, and that even Arcturus here is not a very big star. Antares is a real big star. Maybe you see the Sun, it's a tiny dot here, 1 pixel on my computer, yes. At this scale, it's been long since the Earth is invisible, you know. Of course, makes you very humble, but at the same time, makes you amazed. And this has amazed people for centuries. How is it that such objects, which are so diverse, are all governed by the same laws of mathematics? In this case, for instance, even if that guy, Antares, is so enormous big, so outside of our world, it obeys the same laws of Newton as the planets. Anyway, let's go back to the solar system. And as I said, in solar system, basically is the sun, and the rest is like a perturbation. So now when we enter a branch of mechanics and mathematics, which is known as perturbation theory, I have a system which is like a simple thing plus a small perturbation. And I want to understand that perturbed system. In the case of the solar system, the simple thing is the Kepler view. And the perturbation is the planet-to-planet interaction. And this planet-to-planet interaction, we want to understand how it affects the behavior of the planets. It's a mathematical problem then that you can write. And that's what Newton did. Let's give names to the masses of the planets and the sun, names to the positions of the sun and the stars, and write the differential equation. Mass times acceleration is the sum of the forces. And in this problem, you may even do some other simplifications, like say that the orbits are almost circular initially, which is almost true for most of the planets. And then you ask, what can we say about the motion? One question, for instance, is this thing stable? And this is a question that already Newton was interested in. If I take this equation, what can I say about the solar system in many thousands of years? And Newton was very much worried. Remember, I told you about the mass of the planets in total being like 1/1000 of the mass of the sun. So it means if I want to put a small number in this problem, like the amplitude of the perturbation, relative amplitude, it will be like 1/1000, 0.1%. It's very small. But you know, if you have a differential equation with a very small quantity, and that is the simplest example, something that increases by a very small quantity over time, if you wait long enough, of course, perturbation will be important. If my bank account loses 0.1% every day, after 1,000 days, there's a big problem. And here, because epsilon was about 1/1000, you would expect from the equation that after 1,000 years there would be a huge difference. However, we know from the observations of the ancient astronomers from all around the world that 1,000 years ago the planets were not much different from what they are now. So there seems to be an incompatibility. Actually, Newton believed that his equations alone were not sufficient to describe the motion of the universe. He even thought that probably there was some intervention from God to help arrange the course of the planet and solar system, in a text that is quite debated and a bit obscure. Anyway, as we see, this was a serious mathematical problem, since even Newton felt it so difficult. However, 100 years after Newton, amazing progress had been made by the astronomers, in particular from Germany and France, with the most important steps being taken by Lagrange and Laplace at the end of the 18th century. These people showed by a careful analysis of the equations that the critical time scale was much larger, not 1/epsilon, but 1/epsilon square. This was very difficult theorem, and by the way, it is for this kind of studies that they invented the notion of matrix, which has become so useful in all kinds of fields of science. Why is it that you have to wait 1/epsilon square, not 1/epsilon? Well, the idea is that over a time, 1/epsilon modifications will compensate each other. You remember the analogy of the bank account. In the example of the bank account, you are always losing. So the difference was always going in the same direction. But look at the perturbations caused by the planet-planet interaction. Imagine this is the sun, this is the Earth, and this is Jupiter. Of course, it's not up to scale. Sometimes Jupiter will take the Earth a bit farther away from the Sun. At other times, Jupiter, on the contrary, say when Jupiter will be here and the Earth will be here, on the contrary, it will have the tendency to make the Earth go a bit closer to the Sun. So, all in all, maybe the effects will compensate. And you know, plus, minus, plus, minus, etc. Maybe it will compensate. Which is the best situation for compensation like this to occur? Probably it is when it goes randomly. You know, if I go randomly, 1 times plus, 1 times minus, all in all, the sum will be very small. When will it be random? Well, the idea that they had is that it will be distributed randomly if there are no resonances between the orbits of these various planets. What is a resonance? Resonance is a famous phenomenon in physics when you have some linear relations between critical quantities. Imagine, for instance, and that would be a resonance, that the period of Jupiter would be exactly 12 times the year of the Earth. It means that every 12 years of the Earth, you would see the same alignment again of the planets. And then 12 years later, it would repeat itself. So if on a period of 12 years there is an increase, then there will be an increase and an increase and an increase, and it will diverge. But if after 12 years Jupiter is not in the exact same position as before, then maybe there is no systematic tendency. Resonance is often something that enables catastrophic situations to occur. Famous example is when, when the military group goes over a bridge, they have to stop walking all at the same pace. Because if they happen to walk at the pace which makes the bridge into resonance, the bridge may very well be destroyed by the walk. But if they all walk at different paces, then there is no resonance, it's randomness. Here it's the same. If these planets walk at all kinds of different paces with no relation, it will be stable. That was the idea. So, non-resonance means there should be no linear relations, like no integral relations between the different periods. Otherwise said, whenever you look at the ratio of the times of the years of the planets, it should be an irrational number. Wow. Did we imagine that rationality or irrationality would play a role in the understanding of the planets? Rational number looks like a purely mathematical question. But here we see it played a role in this understanding of the physical world. Let's also notice that, okay, let's keep this, but just focus on this. In those days, the same people, Lagrange and Laplace, they showed that all observations of astronomy that were known could be all explained by the Newton law. So it works even better than Newton himself thought. And it was amazing to think that all observations recorded in human history now could be explained with one law. And it would remain so for yet a bit more than 100 years, or about 100 years, until people discovered that there were slight corrections in the orbit of Mercury that later would be explained by the theory of general relativity. Okay. Let's continue with the problem of stability of solar system. 1 over epsilon square is very long. If epsilon is 1 over 1,000, then 1 over epsilon square is 1,000,000. So that was the conclusion. The planets will remain in about the same state as we know for about 1,000,000 years. Isn't that amazing? They already knew this in the 18th century. But mathematicians are never satisfied with their answers. They always want to have absolute knowledge. And so comes the question, what comes after 1,000,000 years? It is only at the end of the 19th century that this started to be studied with Henri Poincares. You saw him on the picture this morning, he was the guy discussing with Madame Curie on the picture of the Solvay conference. And Poincaré studied a much simpler mathematical model. Let's just take the Sun and one planet and one satellite that will be assumed to have 0 mass, and look at the motion of the satellite and see if it is stable. You know, a simplified 3-body problem. And Poincaré, by some reasoning, very sophisticated, showed the stability for all times, not just a million years, but forever. This is a famous dramatic episode in the history of sciences. So in those days, Gustav Mittag-Leffler, who was a prominent Swedish mathematician, had convinced the king Oscar to announce a big prize in mathematics. And one of the possible subjects was celestial mechanics, and Poincaré participated in the prize with his work and won the prize for his work on the stability of solar system. And the prize was a big amount of money and publicity. It made Poincaré world famous, but also the publication of the winning paper in Acta Mathematica, the journal founded by Mittag-Leffler. And you know, it was not a joke to publish the works of Poincaré, because he had a very messy style, always full of small mistakes and so on. And when the editor prepared for publication, he sent Poincaré a long list of remarks, like you should change this, etc., or there is a problem here and there. Poincaré corrected everything. But still, he kept thinking about it, and one fine day, he discovered, to his horror, that all his proof was false because of a certain key error. It was a problem because the paper was already published, the prize already awarded, and he had got all the big money already for it. Very embarrassing. But Mittag-Leffler kept it secret and claimed back all the copies of the journal, writing to all the people in the world who had it and getting it back and destroying all the copies so that there would be no trace. Poincaré paid for all the expenses so that all the money he had got from the prize and even more was destroyed by this. And then Poincaré reworked the whole thing, and that time could make a completely true theorem, which nowadays is considered one of his masterpieces. Only one difference: now he was not proving stability, but instability, showing that the instability was possible in the long term. Poincaré, on the other hand, discovers that the reason for his mistake is extremely interesting. And in that precise mistake lies the foundation of what would later be called the theory of chaos. And Poincaré understands that it's very difficult to predict the long-time evolution of a mechanical system. You see, Poincaré has these two curves for the system. The blue is represents the state of the system in very far ago, long ago. And the red curve represents the state of the system in the distant future. Whenever the two curves cross, corresponds to stability. But see how complicated these two curves are. And it's very difficult to predict where they cross or not. And a tiny, tiny difference in the initial state of the system can imply a huge difference in the final state of the system. That's one of the main things in chaos theory: extreme sensitivity to initial conditions. Chaos theory would later become a subject on its own, associated with the work of, for instance, Birkhoff, Lorentz. This is the famous Lorentz attractor describing the complicated evolution of a system in meteorology, but very, very much simplified. And the work of Poincaré is that yes, there are situations in which you cannot predict what will occur to the system, On the other hand, he made the fundamental suggestion that you should still be able to make a prediction of what can happen statistically. Maybe half of the time it may be stable, half of the time non-stable. And the idea that even if you don't know what will occur to this specific system, you still are able to make statistical predictions was a bit of a revolution. Okay, it was not the final revolution, however. Wait a little longer, and then arrive the new surprise. Middle of the 20th century with the Russian mathematician Kolmogorov. You know, Stalin died in 1953, and the legend says that Kolmogorov was so joyful with that news that he decided to prove an amazing theorem. And that amazing theorem was the start of the Kolmogorov-Arnold-Moser theory, one of the famous theories in the 20th century. And in those days, people believed that in the end, in the long term, solar system is really unpredictable. But Kolmogorov has this idea that maybe you can assert the stability in a very much likelihood way. Like maybe you don't know, but maybe there is 99% chance of stability. For this, he developed a whole new theory, and he showed that if you perturb a completely integrable system, say this is a simple system and you put the perturbation, and then choose an initial configuration randomly, then with high probability you should stay on a stable trajectory. Poincares had shown that it may be unstable. Kolmogorov said, okay, but I am sure that it is probably stable. And it came with a further refinement of the mathematical sophistication. Let me give you just an idea about it. Let's make a digression about drawing a random number. Kolmogorov tells you that let's draw the conditions of the planets randomly, and then I think there will be stability. What does it mean to draw conditions randomly? Well, maybe you choose randomly the ratio between the year of the Earth and the year of Jupiter. Okay. What does it mean, drawing a random number? You know, there are two concepts that have kept mathematicians and philosophers busy for many, many years. This is randomness and infinity. All kinds of paradoxes. And here is no exception. So taking a random number within the interval 0, 1 means that the probability that it falls within interval AB is B minus A. This is a uniform random number. If you ask a random number to your computer, that's what it's supposed to give you. Okay. With this definition, the probability to hit a rational number is 0, which is very strange after all, because rational numbers are so many. They are dense. Like pi is irrational, but you can approximate it to any degree of accuracy by a rational number. But still, rational numbers are of 0 measure. Now, some numbers are badly approximated by rational numbers. They are called the Diophantine numbers. A number is Diophantine, x, if for any integers p and q, when you try to approximate x by the ratio p over q, the approximation is never too good. That is, the error is always at least constant divided by q to the power r. So these are the numbers which it is not so easy to approximate by rationals. And it can be shown that these very rational numbers are still of probability 1. So in other words, there are 100% of the numbers, even though not all. And Kolmogorov shows that if the ratios between the times of the planets are Diophantine, then they will be robust to perturbation. That's one key of the theory. So you see this and you say, but that's amazing. How would such a tricky, subtle notion be so important for the large time behavior of the planets. That's also a big discovery. Also, you will say, can we have examples of Diophantine numbers? I will say, yes, it's very easy. And for instance, in a way, the most Diophantine number, the one which is worst approximated by rational numbers, is our old friend, golden ratio. It looks so simple, but in fact it's complicated in some sense. And it's ironic, doubly ironic in a way. You know, golden ratio is often thought as something that is harmony, associated with perfect architecture or whatever. We mathematicians actually usually are fed up with golden ratio because many people want to talk about it. And in this case, it is true that golden ratio is associated with harmony. The theorem says that if you have the sun and two planets and their periods are in a ratio of exactly the golden ratio, then this configuration is the most stable that you can imagine for long time evolution. And ironic because it gives you the stability through this kind of randomness. Okay, one problem, so many different chapters and so many different answers. But this was still not the final answer. Okay, let's skip this. And let's go to this. In the 80s, there was a nouveau coup de théâtre in all this. When Jacques Lascar in France, Scott Tremaine in Canada, and other people started to see what happens when you run this on computer simulations. In those days, everybody believed in the stability of solar system after the work of Kolmogorov. Okay, let's check on the computers. When you want to put this on your computer, it's no simple thing. You have to be extremely careful with the approximations. You have even to devise specific numerical methods to handle the errors. And this is what they did. Choice of numerical methods was a big thing. For instance, Jacques Lascar decided to look at the evolution of the Keplerian orbits over time. Like at each time, the orbits are roughly Keplerian, and let's see how they change these ellipses. For this, he wrote down a perturbation system involving 150,000 terms, the kind that only the computer can read, you see. It was polynomial of degree 5. And what was the conclusion of all this? And this was confirmed again and again. In the end, instability. The correct view was not the one of Kolmogorov, but the one of Poincares. The solar system in the long run is unstable because perturbations, even if they are small, are not small enough. Let us watch a small movie by Jacques Lascar that will summarize their discovery. So here, this is the evolution of the orbits of the planets as time goes by. You see the Sun, Mercury, Venus, the Earth, Mars, etc. At the beginning, nothing particular arises. But if you wait for billions of years, there is some chance, a few percent, not completely negligible, that the planets have this kind of behavior, which is not good news at all. It means that after such a long amount of time, collisions between planets become possible. And we have no way to tell if this will occur or not. The only thing we can say is a certain probability, like 5% chance that some dramatic event occurs after a couple of billion years. And it's not that we are stupid, but it's impossible to predict. You see the beautiful collision of Mars with the Earth that maybe someday will occur. Okay. So science sometimes is a mystery, you know, and somehow may be frustrating. Like Newton asked the question, is the solar system stable? And then some of the most brilliant mathematicians of all time worked on this. They invented the theory of matrices, differential equations, numerical methods of first class, symplectic schemes, chaos theory, the so-called Kolmogorov method, and so on. All this sophistication, and in the end, the answer is maybe. But first, as I told you, this maybe is a strong one. It tells you, yes, there is a definite probability. And second, all the scientific progress which has been made from that is very important. Many of these topics which were developed first in the context of the solar system then were applied to many other problems in mathematics, engineering, physics, and so on. And that is always the thing about scientific progress. It goes in all directions. Now, this is the most famous of all problems in long-time behavior in classical physics, stability of the solar system. I did not work on this problem in particular, but on another problem which has some similarities and some differences, and which is very easy to understand. What about the stability of a galaxy? A galaxy can be made of 100 or 1,000 billions of stars. See how difficult it was to understand the behavior of one star plus 8 or 9 planets. Will it be 1 billion times more complicated to study a galaxy? Maybe, or maybe not. In mathematics, sometimes large is good news. Like, you know, if you have to toss a coin and your life depends on whether it is head or tail, it's a very dangerous situation. But if you can toss the coin many, many times, you know what will occur. About 50% heads, 50% tails. That's the power of large numbers. They give you more predictability through the statistics. So if a galaxy is made of a large number of stars, maybe this gives it much more predictability. Maybe in the end it will be easier to study this. This was the idea of people who first studied galaxies. It was the idea in particular of genes that to this problem one could apply the statistical mechanics defined by Maxwell and Boltzmann. Maxwell and Boltzmann were interested in the description of gas. Gas is made of molecules, and there are many, many molecules in a gas. At the scale of a galaxy, because there are so many stars, maybe we can apply the same theory, the so-called kinetic theory, because you are interested in the statistical distribution of velocities and positions. So let us, rather than writing down or thinking of the thousands of billions of stars, think about the statistical description of them. And it's a statistics that depends on variable velocity and position. Like there is that proportion of stars which are fast, that proportion which are slow, etc. And from that statistics, you want to understand what will occur. So we need an equation of evolution, a differential equation. The most famous differential equation for statistics of gas is the so-called Boltzmann equation. There it is. Even for mathematicians, it looks a bit frightening. I remember when my PhD advisor first wrote it down for me, my thought was, maybe it is time to change subject. It is an old equation, 150 years old, and it describes the evolution of a gas inside a box through the action of random collisions. Boltzmann made an amazing discovery with this equation. He discovered that if you introduce a quantity that he called the entropy, well, entropy was known before from thermodynamics, but he had the idea to give a statistical meaning to this entropy and to see how it evolves under the action of the differential equation, and he discovers that the entropy was always going up, thus giving a mathematical justification of the second law of thermodynamics. And a conceptual revolution that this law of thermodynamics would be based on probability, not on certainty. This was a conceptual revolution that even Maxwell did not believe. In those days, people knew that entropy was always going up, but everything that was an absolute law, they thought, should have absolute fundamental reasons, not probabilistic reasons. Boltzmann also understood that you can always define entropy for any system as soon as there is an observer. If there is an observer with a partial information of the system, you call W the uncertainty, what you cannot observe, and the logarithm of that uncertainty you call the entropy. This is his most famous formula. S is k log W, and it changed our whole understanding of the world. The idea that everything among us is determined by the fact that in our world there are a lot and a lot of random motions of tiny invisible particles occurring, the basis of atomic hypothesis. The Boltzmann formula is written on his grave in Central Cemetery in Vienna. And by the way, as I always tell, this was a picture of taken 100 years after Boltzmann's death. I was in those days invited to a conference in Vienna in the honor of Boltzmann as one of the recognized specialists of entropy. And I thought, you know, after all this time I spent on the Boltzmann equation, he is like family, I have to pay a visit to him in the cemetery. Arriving in the huge cemetery, I discovered that it was enormously huge and that I had no idea where was his tomb. It was in the evening. I asked my way to some family sitting nearby. Hello, do you know where I can find a map of the cemetery with the names of the famous people? And they said, there is no map. Who are you looking for? And I said, Boltzmann. Ah, and the guy looked at me and answered, S is k log W. There it was. We were members of the same sect, after all. And S is k log W really is a huge, of huge importance. Entropy now is all around us. Entropy plays a key role in explaining the physical laws of the world. Like, think of this. Imagine if you put gas in a half of a box and let the gas free to move. What will occur? We all know what will occur. The gas will invade the whole box. And we think of it, things like maybe vacuum sucks the gas in. Boltzmann tells you it's not about a force attracting. It's about probability. It's because in this configuration the entropy is much higher because the uncertainty is higher. Because you don't even know if the gas will be on one side or the other side. And spontaneously the gas will search for a state which has the maximum of entropy. So it gives you a new view on all the physical phenomena in the world occurring due to so much randomness in many situations. In science, as long as you have one answer, it introduces new questions, which is why the number of questions in science keeps increasing year after year. So once you have this answer, entropy is always increasing. A new question occurs. What will be the final state? Maximum entropy. And this the people did at the time. And they found that it is the same law which appears in the law of large numbers, the Bell curve, the Gauss curve, which ultimately describes the velocity distribution of the particles. Okay. Isn't it amazing to see this absolute law emerge from the randomness? Then, thinking back about our problem of galaxy, we may think, but that is the answer to our problem. Because in the galaxy there are so many stars, in the long run it will converge to a state of maximal entropy. And the velocities will have this distribution. And the positions will be kind of uniform, as in a gas. People believed this for some time. Until a new change. In the 60s, astronomer Lyndon Bell pointed out that this could not be the explanation. Yes, maybe a galaxy is in some kind of equilibrium. But if we wait for the collisions to do this, and collisions are the key in Boltzmann equation, it will take too long time because the collisions are rather rare. You would have to wait for thousands of billions of years. So there has to be another explanation. And it should not be based on Boltzmann equation. It should be based on a collisionless equation. Lyndon Bell coined the oxymoron, the paradoxical word, violent relaxation for this. The idea that in certain systems, even if there is no entropy increase, there will be relaxation spontaneously. That was a tough cookie for people to accept. So he had to argue. And to argue, he said, it will be like in the Landau damping in plasma physics. Landau damping in those days was a recent discovery. Named after the Russian genius Lev Landau, it is the idea that in a plasma, which is like a crowd of electrons, there is stability even without collisions. This is a picture of Landau. By the way, he doesn't look happy. That's normal. It's a mugshot, In those days, in that regime, you could be arrested for no good reason and sent to Gulag or be executed just because you were a good scientist but with dangerous ideas. And Landau, however, was released from prison thanks to the courageous action of his colleagues. And after that, he made this extraordinary work on plasma, showing that if you take a plasma which is at equilibrium and perturb it a bit, spontaneously equilibrium will be restored. These are plasmas. It's a state of matter in which electrons have been freed from the nuclei. And this is the mathematical equation behind it. And it turns out that the same equation is also used for galaxies. So we should think of galaxies not as analogous to gas, but analogous to plasmas in which collisions are very rare and entropy remains constant. Okay, but was the reasoning, the theoretical reasoning of Landau really right? There was some controversy. In particular, because Landau's computation was only for a simplified equation, a linear equation. The equation that I showed here is nonlinear. F is the unknown, and F appears here twice, so the equation is quadratic. Quadratic equations may be complicated, so he replaced it by a simplification which is linear, and then made a lot of mathematical reasoning. Can we make a mathematical justification of this? It was not clear. And over the years, people gave different answers until eventually, with my former student, Clément Mouot, I could solve this problem, at least in the mathematical world, and showing that, yes, even for the nonlinear equation, there is this stabilization in large time. Let me say just a few words about one idea that we showed which was key. What mathematicians like most is finding new relations between various problems. And we discovered there is a strong link between three problems in classical mechanics. One is the Landau damping in the nonlinear regime, so a tiny perturbation of a plasma system in large time. One is the Kolmogorov theorem that I told you about perturbations of ordered systems. And the other is the so-called plasma echo experiment. You take a plasma which is at rest initially, so force field is 0. You make a small perturbation for an instant of time, and you let the plasma evolve. Force field will go spontaneously to 0. Then you make a second perturbation at a different frequency, and you let it evolve. It will go back to 0. And after some time, you will hear an echo, that is the force field will again spontaneously be non-zero. This is called the echo. It's a famous paradox. And it shows you, among other things, that plasma react with delay. We discovered that this delay is fundamental in the stability in the long run. And this was new, even from the physical point of view, let's say. Okay. Then it was no joke, so I have to say. This, by the way, is the fundamental state of the usual mathematician, spending his life or her life in perplexity. I tell you, however, even in this state, we are happy. At the same time, frustrated and happy, because entirely immersed in the problem and thinking, God, I am stupid, but I will find. Fortunately, you're not alone. Most of the time, you work in collaboration. In this case, as I said, my former student, Clément Mouot, was an amazing collaborator. There was need of the two of us. Otherwise, it was impossible for a single individual, I believe. So much were the difficulties. It's like when you are climbing the mountain. You know you have to be two. Let me also say that this is a frustrating process, mathematical research. Very difficult, in which you make so many mistakes and wonder. But it's passionate also. Actually, in the book that was alluded to in the introduction, for broad audience, I told it like a novel with all the difficulties and the mistakes and the travels and the discoveries, the 2 years of wonder and so on. Even putting some of the mathematical sophistication to give the readers an idea of what it really looks like. And people, even those who did not care of the result and have nothing to do about the long-term stability, were fascinated by this process, the fascinating life of mathematical research, scientific research in general. It's a fascinating thing. Okay, in the end, this was the result. A 180-page paper full of good mathematics, and all to prove just one theorem. When you look at this, you say, how is it possible? But when you are in it, you don't care. Actually, when you are the author like me, when I look back at this, I think, how was I able to write this? I don't understand. When you are in the middle of the effort, you make things that are much above your natural capacity or what you believe you are able to do. And that's what gets you the awards. So this was a long mathematical proof, ending up a long controversy. The first result of nonlinear relaxation without entropy increase, and identifying some factors in the physical world and mathematical world, like key role of some regularity features in this. As was mentioned, this was also one of the key results behind the Fields Medal received in 2010. And let us, however, insist that when you receive an award, it's not so much for what you have solved than for what you have started. And this result, if it was just one result and the end of it, would not have been so great, I believe. But it was source of inspiration for later work. And that's what we like in science. You do something, then other people can use what you do, and you have much more offspring than what you alone do. So, for instance, two brilliant mathematicians, Bedrosian and Masmoudi, using our tools, our ideas for the stability of the plasma or galactic equations, managed to solve another problem, which was the stability of so-called shear flow in fluid mechanics. That is, when you have the velocity profile of a fluid, which is a perturbation of this linear profile that is written here. Think of this as the velocity of a fluid that is infinite in 2 dimensions. And it was a question asked for a long time, even by people like Kelvin or Rayleigh, about understanding the stability of these things, even when there is no viscosity. Viscosity for a fluid is a bit like collisions in a gas. It gives the friction. And it was also a famous problem in this? And the answer was yes. Again, they used our ideas, they added more ideas, and from that they deduced new results about stability of fluids, two-dimensional turbulence, and so on. And so that's also the other thing I wanted to say. At the same time, research is about this huge collaborative effort of thousands and thousands of people in the world. You do something, other people use it. And still, in spite of all this, one should always remain humble. It's all a droplet. Even this that I showed you, for instance, this big result about the perturbation of a galaxy is a droplet compared to what you would like to say. Think again about the movie that I showed you with the galaxies doing this and that. Do we understand it now? No. Now we understand just a tiny thing, which is perturbation of equilibrium. Did it look like perturbation, the movie that I showed you? No. Nobody knows what occurs when it is in this non-perturbative setting. So it means so much more, and probably centuries of good work to be made from various points of view on these problems. Thank you.